All right, so last time we talked about derivations and differentials. So later today we'll talk about Lie algebras. So just to review some of the things we did last time, because they'll be important for today. Hopefully you got a chance to internalize some of these concepts if they're new to you. Okay, so we have a notion of a derivation. So if we have a commutative ring and an algebra over that commutative ring, and a module for that algebra, then a derivation is a linear map, an R linear map from A to the module that satisfies the Leibniz rule. So if we have a product of elements in A, we have this relation. So dB and dA both live in the module, and we act on them. So this juxtaposition here is acting of A on M. And we had examples of derivations, so derivatives of, this should be a capital T here, the derivative of polynomials, the partial derivative of polynomials in multiple variables, those are all derivations. And then we saw these basic facts that derivations vanish on the ring if there are derivations, and they form a module structure coming from the module structure on M. So their derivations are an A module. And anytime we have an algebra homomorphism, we get this exact sequence of maps between modules. And we saw also as an example, if we have just the polynomial algebra and variables, then as a module, it's the free module on the partial derivatives. So the derivations form a free module with generating set given by the partial derivatives. And then we were investigating what happens if we have an algebraic set inside AN, so the vanishing set of an ideal. We might as well assume it's a radical ideal. So in particular, the derivations from the affine algebra of this algebraic set to some module for the affine algebra are a submodule of the derivations from the affine algebra of A to the N, so polynomials, into this module N. And then we talked about tangent spaces. So how do we define the tangent space? So first of all, we thought about tangent spaces in the embedded setting. So when we have a algebraic variety that's realized as an algebraic set inside of A to the N for some N. So what is the tangent space? And we argued that the tangent space is, so intuitively speaking, it's everything that's orthogonal to the gradients evaluated at a point for all the functions in the ideal. So one way to think about this is as following. So if X has dimension D, say, then this ideal has D linearly independent generators. So that's, I think this was something I mentioned so that's coming from algebraic geometry. I think I mentioned that when we reviewed algebraic geometry in the first week. So we have D polynomials F1 through FD that define X. And we can compute their partial derivatives with respect to the N generators of the polynomial algebra, so T1 through Tn, the coordinates on A to the N. And so what we can organize this into a D by N matrix. So we have D generators and then N partial derivatives for each one. And so we have a matrix of polynomials, matrix where every entry is some polynomial. And if we want to compute the tangent space at little x, then what we do is evaluate all these polynomials at little x. We get some matrix of numbers and we take the kernel of that matrix. So the kernel lives inside n-dimensional k to the n. So that's another way to think about this. And yeah, I'll mention something more about this interpretation later on. But from this description of the tangent vectors being the ones orthogonal to the gradient at a given point, and orthogonal to all these gradients for all the polynomials in the ideal, we deduce that this definition of the tangent space as derivations from the affine algebra to k little x. So this is the one-dimensional module given by quotienting out by the maximal ideal of all polynomials that vanish on little x. Okay, and this is a intrinsic definition, so it only depends on the affine algebra of x, as opposed to embedding it into some a to the n. Okay, so that was the definition of tangent space. So this is what we'll use, is these derivations. And so there's basic facts that are analogous to the tangent space from differential geometry. So we get a differential for any time we have a morphism of varieties. We get a differential from the tangent space of x to the tangent space at the image of x. And this map is just precomposition by the associated algebra homomorphism. So yeah. So that's that, and we have the chain rule. So the differentials respect composition, and yeah. So those were technically, we need to do those first for affine varieties, but then we can extend everything to non-affine varieties. And then there were some basic facts, like if we have an open inclusion of a subvariety, then the differentials at all the points of x are isomorphisms. And if we had a closed inclusion, then the differential is injective at all the points of z in this case. And there was some, so you've probably seen some other definitions of the tangent space, so they're all equivalent. So one is as the dual space to mx mod mx squared, mx being the ideal of the affine algebra. So mx includes inside of the affine algebra as the ideal of all functions that vanish at little x. And if we take those up to first order, so if we mod out by mx squared, then we get this quotient. So that's actually the one forms at x, at little x, and the dual space is the tangent space at little x. And we can also think about it as the following. So we have this local ring at every point little x. So it's obtained by localizing the affine algebra at everything outside of this maximal ideal M. We talked about localization procedures in the first lecture, and that has a unique one-dimensional module because it's a local ring, so it has a unique maximal ideal. When we quotient, you get just K, and these derivations give you another definition of the tangent space. All right, and yeah, and so then there's this notion of smoothness. So if we have so the right adjective here is connected. So if we have a connected algebraic variety, we say that it's smooth at a point if the dimension of the tangent space is equal to the dimension of x. So I think I was a bit confused about this before because I said irreducible. In fact, that's not quite the right thing. So we just have to be connected. So different connected components can have different dimensions, and we can have smooth points, and the smoothness of a point just depends on which connected component it is. All right, and the variety x is smooth if it's smooth at every point. So if the dimension of the tangent space is equal to the dimension of x at all the points. So to kind of internalize this definition, you can think about these examples that we saw before. So this first one is not smooth at 0, but it's smooth everywhere else. The second one is smooth everywhere. You can also think about x squared plus y squared, or just y squared minus z squared. Those are just simpler examples. Okay, and then I said this theorem here. So if x is irreducible, dimension d, then the smooth points of x form a non-empty open subset of x. And the dimension of the tangent space at any point is bigger than or equal to the dimension of x. So one way to think about this theorem is using what I said before. So if let's say x is embedded, it's affine and it's embedded, and it's cut out from a to the n by d linearly independent polynomial is f1 through fd, then you take all the partial derivatives and you form a d by n matrix. And so since the f's are linearly independent, this matrix will be generically a full rank. And that's why these smooth points form a non-empty open set, because you have something of a full rank. So its kernel has the right dimension. So if you work out the dimensions, you see what the dimension of the kernel will be D. And so, yeah, so I won't go through the details, but that's kind of some intuition about why this theorem is true. But the kernel could be bigger, which means that the dimension of a tangent space at some point could be bigger than D, the dimension of X. All right, so that's this theorem, and we used it to deduce some basic facts about algebraic groups. So first of all, algebraic groups are smooth, and any homogeneous space for an algebraic group is also smooth. And any map between G-equivariant map between homogeneous spaces has constant rank. So the rank of the differential at any point is the same as a linear map between finite dimensional vector spaces. So we had that, and let's see, then I think we talked about Euler differentials. So so same sort of setup. So just to be, for simplicity and to anticipate some things, that's A is now a commutative R algebra, and we defined the Euler differentials in this way. So we took the multiplication map on A. It has some kernel, so it's an ideal, and we define the Euler differentials as I mod I squared, where I is this ideal. So yeah, another way to think about this is if A is an affine algebra, so it's the affine algebra of some variety X, then A tensor A is like functions on the product X cross X, and this ideal cuts out the diagonal of X cross X, and these are sort of like functions that are supported on the diagonal up to second order terms. So yeah, maybe let me not be too precise about that, but there's a geometric interpretation of this too. And another definition of the Euler differentials well, let me mention it in a bit. So this ideal is generated by A tensor 1 minus 1 tensor A for all the elements in A. And it has a natural structure as an A module. And there's a map from A to the Euler differentials that take A to dA. And this map is surjective. And so we can think of the Euler differentials as the free module generated by these modulo some relations. And what are these relations? Well, they will actually be the Leibniz rule. So the relations will be D of the product A times B is A times dB plus B times dA, where times is the module structure. Okay, so that's another definition of Euler differentials that maybe you've seen in other places. It's equivalent to this one. And the one of the important basic facts about Euler differentials is that they encode derivations in the following way. So if we have any A module M, then if we want to understand derivations from A to M, so we saw that these derivations are related to tangent spaces, there's some geometry going on. If we want to understand those derivations, then those are the same as A linear maps from the Euler differentials to M. So Euler differentials are an A module, M is an A module. We can think about A linear maps, and those are the same as derivations. So sometimes derivations are a bit tricky to understand or a bit non-intuitive because of the Leibniz rule, but A module homomorphisms are maybe a bit simpler to understand. On the other hand, these Euler differentials are kind of big, so that may be a bit unwieldy. but yeah, but we get this isomorphism of A modules. So yeah, a categorical interpretation is that the Kähler differentials represent this functor of derivations. Okay, so we talked about the proof, and yeah, so just like with derivations, well, okay, anytime we have a R algebra homomorphism between two R algebras, then we get a linear map between the Kähler differentials. So yeah, the A module structure and the Kähler differentials on B is coming from this homomorphism. And we have the following commutative diagram. So D of little a just goes to D of the image of little a, D of phi of a. Okay, and so for the polynomial algebra, derivations turn out to be very simple. So derivations to any module are just n copies of that module because everything's determined by where T1 through Tn go. And yeah, and then we had this proposition. So this proposition looks kind of technical and abstruse, but it's actually very useful for computing. So it's basically saying that if we have, so A is a quotient of the polynomial algebra in some number of variables. Then if we want to understand the Kähler differentials for A, then it's a free module on the images of the, on D of the images of the generators of the polynomial algebra, modulo some relation, and the relations are given by some partial derivatives. So we have to take, we look at things in the kernel, so in the defining ideal of A, and we take some partial derivatives and we form this expression, and we take the module generated by all these expressions over all the elements of the defining ideal, and we get a submodule of A to the n, and we quotient by that, we get the Kähler differentials. So yeah, so then we proved it, and we talked about the example of SLN. So we use this somewhat technical proposition to compute the tangent space at one of SL2, and so we got that it's three-dimensional, as we already know, since SL2 is three-dimensional, and it's smooth, and it can be described as 2x2 matrices with trace 0. And we'll return to this example later in today's lecture. And I guess in the TA session, Shivi talked about why you can identify the tangent space at the identity for the orthogonal group as all matrices that satisfy m plus m transpose is equal to 0. So yeah, okay, so that's quite a bit of material. Any questions on this stuff from last time before we go on?
Is there like a relation between non-smooth points and like can the color differentials detect non-smooth points somehow? Do these affect them?
Yeah, so for smooth points, when you specialize the module to the point, you get something of the right dimension, and for non-smooth points, you get something of bigger dimension. When you, it's a matter of specializing that module to the point, taking the tensor product with k little x.
And also about the exact sequence of derivations.
Yeah.
It was exact from the left. Do you have an example where it's not exact from the right?
So it's, I believe this happens when the map is not flat. So I think if you have a flat map, it's exact on the right. I meant to double check this, but I believe that's the case. So if you have some map that's not flat, so maybe some of some blow up map, then yeah, but the blow up maps won't be given by affine algebras. Yeah, so I don't have an example right away, but if you have an example of a map that's not flat, I believe you can see that it won't be surjective at the end.
Okay, thank you.
Mm-hmm. Okay, any other questions? All right, so let's move on. Here we go. So the algebras. All right, so first of all, well, actually, first I had to compress the file to put it on the website. So if there's any problems with the resolution of the file that's on the website, let me know. I can try to fix it somehow. Not right now, but later. All right, so Lie algebra. So first of all, what's a Lie algebra? Maybe some of you are already familiar with this definition. So it's a vector space over K. So K continues to be an algebraically closed field. And we have a bilinear operation from G tensor G to G. And this operation satisfies two properties. So first of all, there's skew symmetry. So if we take the arguments in reverse order, we get a minus sign. And second, the Jacobi identity. So if we do the cyclic permutation of the entries and we sum everything up, then we get 0. So so that's a Lie algebra. So we'll see examples soon enough. And it's we say it's commutative if it happens to be the case that this bracket is just 0. So it's just 0 for all vectors x and y. So the idea of Lie algebras and the connection to linear algebraic groups is that we'll associate a Lie algebra to every linear algebraic group. And a lot of the structure and representation theory of the group will be reflected in the Lie algebra and vice versa. So roughly speaking, we'll have we'll have exactly this map from linear algebraic groups, this assignment, let's say, from linear algebraic group to finite dimensional Lie algebras. This assignment will be roughly finite to 1. We'll say more about that later. And we'll see how some geometric methods on the group side can be translated to algebraic methods on the algebra side and vice versa. So sometimes, we can get some insight from the Lie algebra that we couldn't get from the group or the other way around. Right, so that's kind of the motivation, and this is where we're headed. So first of all, some more facts about Lie algebras. So anytime we have an associative algebra, we can produce a Lie algebra in maybe a somewhat stupid way. So if we have an associative algebra, let me call it E. I wanted to reserve A for commutative associative algebras. So E is just some associative algebra, doesn't need to be commutative. Then it has the structure of a Lie algebra in the following way. So the bracket of two elements x and y inside of E is the commutator, so xy minus yx. And we see right away that it's commutative as an associative algebra if and only if it's commutative as a Lie algebra. So associative algebras can be regarded as Lie algebras in this way. So you can check the axioms if you want practice with the axioms, you can check that they're satisfied in this case of Lie algebras coming from associative algebras. So you can think of this construction as a forgetful functor. So we're forgetting some of the structure of an associative algebra in order to produce a Lie algebra. So forgetful functors are often right adjoints. They have left adjoints, and we'll talk about the left adjoint, which is a sort of free functor later on. So that's kind of an aside for those of you who are taking Rami's class. So what are some examples? So if we have, let's start with an associative algebra, namely the algebra of endomorphisms of a vector space over K. And so if we take the corresponding Lie algebra structure with the commutator, then that's a Lie algebra, and it deserves a special name because we'll see it later. It's GL of V. So I'll write GL of V when I want to think of these endomorphisms as a Lie algebra as opposed to an associative algebra. So that's just some notation. Okay, so let's think about some Lie algebras that we get from this endomorphism algebra. So let's think about the subspace of endomorphisms with trace 0. So maybe I actually want V to be finite dimensional here. So if we think about things with trace 0, then this is not a associative subalgebra. So if we take two matrices with trace 0 and you multiply them, their product won't necessarily have trace 0, but it is a Lie subalgebra. So it's closed under the bracket, and that's because the trace of two matrices is the same regardless of which order you multiply them. So yeah, trace of f times g is equal to trace of g times f for any two endomorphisms. And yeah, because of that, this is a Lie algebra, but it's not an associative subalgebra. So it's kind of, in some sense, it's easier to be a Lie subalgebra than it is to be an associative subalgebra. And yeah, traceless endomorphisms are defined independent of any basis, and they do not form an associative algebra, like I said. Okay, and this Lie algebra is also special, and it also deserves a name. Let's call it SL of V. So we'll see why this is the right name later on. So, okay, what about a different example? So let's take R to be a commutative ring and A to be an R algebra, also commutative. Yeah, maybe A doesn't need to be commutative, but let's just say it's commutative. So then we thought about derivations from A to some A module M. Let's take that A module to be just A itself. So let's look at derivations, R derivations from A to A. So these are in particular R linear endomorphisms of A. So a derivation is in particular an R linear map, so it's in particular something in here. Moreover, we claim that this is a Lie subalgebra of the endomorphisms, R linear endomorphisms of A. And that's just an easy check. So if we have two derivations, you can just go through and check that this difference of the compositions in different order is again a derivation. So again, this is another example where we have a Lie subalgebra of the endomorphism algebra of an associative algebra that's not itself an associative subalgebra of the original algebra. So the Lie algebras that we'll see later today and in this class, they'll usually be coming in this way. So we have some associative algebra with kind of the stupid Lie algebra structure just given by the commutator. And then inside of there, we'll identify some subspace that's not an associative subalgebra, but it is a Lie subalgebra with the commutator. Okay, so let's elaborate further on this example. So let's say we have R, again, a commutative ring, and A an R algebra. And let's suppose that a group G acts on A by R algebra automorphisms. So we think of G as mapping into the general linear group for A, and with the condition that every row of G is a R algebra automorphism. I could have put also GO sub R here, but it's an R linear map that's also automorphism of the algebra structure. Okay, so in this case, we get an action of G on the R linear endomorphisms of A in the following way. So if we want to, so this is a standard thing. So if we want to know what G does to an endomorphism F, Well, we first precompose by the action of G inverse, and then we act with little g on the image. So if we have an element A, then what we do is we do G inverse of A. So really what I mean by G inverse of A is the is rho of G inverse. So I'm being a bit sloppy with notation here, but it's rho of G inverse. That's algebra automorphism of A. And then we apply F. F is our just any linear map from A to A. And then we apply rho of G. So again, this G just denotes rho of G. We apply that to the output. So so that's an action. And so a few claims. So first of all, if we think about the endomorphisms that are actually derivations, then they're stable under the G action. So it's a G subspace. So G takes any derivation to another derivation. So that's where you use the fact that G acts by algebra automorphisms. So that's one fact. And the other claim is that if we think about the G invariant, endomorphisms or the G invariant derivations, then those are Lie subalgebras. Yeah, so they're invariant, but you can also think of them as kind of equivariant as endomorphisms. So yeah, there's this kind of semantics that, like, if you have something that's, if you have G acting on two G representations, then their HOM also has a G representation structure, and the invariants in the HOM are just the equivariant maps. So I might use invariants and equivariants, invariant and equivariant a bit interchangeably. So yeah, so the claim is that if we look at the ones that are fixed by the G action in both all endomorphisms and those that are derivations, then we get Lie subalgebras. And that's, yeah, so when you check this, you see that there's some cancellation that happens, and we get what we need. Okay, so everybody good with the basic definitions and basic examples so far? Okay, so just like in the last lecture, there's a lot of kind of relatively simple things to check, like sanity checks to make sure all the concepts are clear. But yeah, these are easy things, so I haven't written out the proofs in the notes. All right, so a few more definitions. So a morphism of Lie algebras is a linear map that respects the bracket. So so if we have G and H Lie algebras, then if we have two elements in G, then a linear map from G to H is a morphism of Lie algebras if, when we take the bracket of those two elements and then apply phi, we get the same thing as if we had taken phi of the original two elements individually and then applied the bracket in H. So the bracket in G maps to the bracket in H. And the representation of a Lie algebra is a morphism of Lie algebras from G to GOV. So again, GOV is endomorphisms of V thought of as a Lie algebra through the commutator. So the commutator of elements in G goes to the commutator of matrices here. Yeah, so those are basic definitions. Okay, so now let's relate things to a bit of geometry. So let's take an affine variety X. So the affine variety has an affine algebra functions, k brackets x, and we can think about vector fields on X. So vector fields are defined as derivations from the affine algebra to itself. So derivations from k bracket x to k brackets x. And as we saw in one of the examples we discussed just now, these derivations form a Lie algebra. It's a Lie subalgebra of all endomorphisms of the affine algebra. And that Lie algebra is the Lie algebra of vector fields on X. And the space of one forms is just the Euler differentials of the affine algebra. So if we have any, so these relate. So if we have any point in X, then we see that the tangent space would just be the tensor product of derivations with the one-dimensional module at X over the affine algebra. So the vector fields are K brackets X module coming from this last factor here. And when we tensor over K brackets X with K little x, then this goes away and we just get, in its place, we get the one-dimensional module K little x, and that's exactly the tangent space. So that's all that's going on here. And similarly for the one forms. And we have these sort of evaluation maps. So anytime we have a derivation, it lands inside of, when we apply it, it's a map that lands inside of K brackets X, but then we can evaluate that function at little x to get an element in the field. And this composition will be a derivation from K brackets X to K little x. So I claim that there's a well-defined map from vector fields to the tangent space at any little x. And this is just given by post-composition with the evaluation map. Hopefully that's clear. And similarly, we get a map from the one forms to the cotangent space, and the cotangent space is the dual to the tangent space at any point. So this is adaptations of differential geometry concepts. So this was about varieties. Now let's infuse things with a G action. So let's introduce a linear algebraic group G and an action of G on an affine variety X. So then, as I guess we discussed in one of the earlier lectures, anytime we have a linear algebraic group acting on an affine variety X, we have several things that are given to us. So we can think of this action in terms of an action map, G cross X to X. And this action map has a pullback. So the associated algebra homomorphism on the affine algebras that goes in the reverse direction. So we get a map from K brackets X, an algebra homomorphism from K brackets X to K brackets G tensor K brackets X, given by the following formula. So this is just the pullback of the action. And you can think of this as a co-action of K brackets G as a Hopf algebra. So so we have this A star, and we also had these maps rho and lambda. So we get a representation of G on the affine algebra in the following way. So G goes to this algebra automorphism rho sub G that's defined in the following way. So it takes a function to a new function that first acts by G inverse and then then applies the original function. So we see that rho of G is just AG, the pullback of AG, where AG is A little g is this act by G map. So we had the act by the whole group map, but if we take a little g, then we have this. So this is the restriction of A to the singleton G cross the singleton little g cross X to X. And if we take the associated algebra homomorphism, that's related to rho of G by taking the inverse here. So we have to have G inverse. Okay, so this is pretty clear, I think, from the formulas. We also had lambda, so maybe I didn't write it here, but we also had a lambda that acts, that it's given by the same formula, except instead of G inverse X, we have XG. So yeah, so we had that. So this is just reviewing some notation. If we have, so in this setting, we can define the G-equivariant vector fields on X as the endomorph, so this is, everything is happening inside of endomorphisms of the affine algebra. So it'll be the derivations that are G equivariant or invariant, depending on how you look at it. So as we discussed in one of the examples above. So those that commute with the G action, those derivations are, we can think of them as, so their geometric interpretation is as G equivariant vector fields. So yeah, if you want to be a bit explicit, it's all the derivations from theta from kx to kx, such that if we first do rho G, then apply theta. So rho G is an algebra morphism of k brackets x. That's the same as first applying this derivation and then applying rho G to the output. So, and this has to be true for all the elements in G. And we can also, since rho G is related to A star of G inverse in this way, we could have put A star of G inverse there if we wanted to. All right, so those are the equivariant vector fields. And as an example, so probably one of the simplest actions is GM, the multiplicative group, acting on C, I guess I put C here, but it really should be K, the one-dimensional vector space by scalar multiplication. So this is kind of a very easy action. And then if we compute what happens on the affine algebra, so the affine algebra in this case is just polynomials in one variable, and it's given by taking t, so it's determined by taking t to lambda inverse times t. So we have our variable that generates the algebra. It goes to multiple of itself, scalar multiple of itself, and that scalar is lambda inverse. And we can note here that, okay, that's what happens to t. What happens to t squared? Well, we get a lambda to the -2 here times t squared. And in general, if we have f that's a polynomial that's homogeneous in t of degree n, then, so it's really, so in this case, that means it's just a scalar multiple of t to the n. Then this rho acts by, sub lambda acts by multiplication by lambda to the -n for any lambda in the group. So that's, yeah, so, and that's if and only if. So now how do we compute the equivariant derivations? Well, first of all, what's a derivation? Well, since this is just a polynomial algebra, any derivation is just the partial derivative. We saw that that's a derivation, or I guess in this case, it's just a straightforward derivative, not a partial, and times some function, some polynomial. So it's any derivation is of this form. So we compute. So what's the condition for this derivation to be in here? Well, it has to commute with these rho sub lambdas for all the lambdas. What does lambda do here? Well, it just, yeah, so, and in order to, yeah, so another thing to note here, in order to figure out this condition, it's enough to check it on on t, on the generator. What does rho lambda do to t? It just multiplies it by lambda inverse. What does it do to the image of t under this map? Well, the image of t is the derivative of t with respect to t times v. So it's just v, and so if we yeah, so we get this, but on the left hand side, if we keep going, then we get the lambda inverse times v. Because we take the derivative here, we just get the lambda inverse. And this has to be true for all lambda. And this means that v has to be homogeneous of degree 1, because it says that this rho g acts by scalar multiplication of lambda inverse. And as we observed before, that only happens to the things of degree 1. So in other words, v has to be in the span. So by this notation, I just mean the span of T as a vector space, one-dimensional vector space inside of the this polynomial algebra. And so that means that the D is just a scalar multiple of T times del over del T, T times the derivative operator. So this is known as an Euler operator. Maybe you've seen it in some other classes. And yeah, it's like a grading operator, and those are the only, so in particular, if we look at all the vector fields, it's some infinite dimensional space, but if we look at the equivariant ones, we suddenly just get something that's one-dimensional. So yeah, so that's this example, if you want an extension, you can think about the scaling action on k to the n. So k to the n is a vector space. It has a scaling action of gm, like sort of diagonal scaling of each coordinate. And you can think about what the g equivariant vector fields are in that setting. So the computation is somewhat similar to what we just did. You can also think about well, yeah, we'll get to other examples later in the lecture. Okay, so that's the notion of an equivariant vector field. So now we have this proposition here. So let's say we have just as before, we have a linear algebraic group acting on an affine variety, X. And so now the claim I want to make is that a vector field on X, so something in Tx, a derivation from k brackets x to itself, belongs to, is G equivariant, so belongs to the equivariant vector fields, if and only if we have the following formula. So what is this formula saying? Well, I don't know if I explained the notation. Maybe I forgot to explain the notation. So theta sub little x, that's the evaluation of the vector field at a point little x in X. So so we have the derivation from k brackets x to k brackets x, and then we have the evaluation map to k sub little x. That composition is theta of little x as a derivation. And so that lives inside the tangent space at little x. Similarly, we have this guy here who lives at the tangent space of g times x, so the image of x under the g action of little g. And we have this a sub g, which is it's a map that from x to x that sends little x to little g times little x. And if we take the derivative of this map, we get a map on the tangent spaces. And I claim that tangent vector defined by theta at little x goes to the tangent vector defined by theta at g of x. So in general, it's some other vector in that tangent space, but it turns out to be precisely that vector given by theta. So I don't know if that made sense. If you've had differential geometry, then maybe it's clear what I mean here. And the second claim is that this is the equivariant vector fields are Lie subalgebra of all vector fields. And the third claim is that if X happens to be a principal homogeneous space, so a torsor for G, then the equivariant vector fields are determined by their value at a point. So if we take any equivariant vector field and we evaluate it at a point, so then we get a tangent vector at some point, that determines, that's an isomorphism.
It's a principal homogeneous space? Like it is transitive?
Yeah, transitive, no stabilizers.
Mm-hmm.
Yeah. So yeah, so I think it's time for a break. So let's resume after the break with proof of this theorem and any questions, any other questions you have. So yeah, so 5-minute break. All right, so any questions from the last few pages of the notes? Okay, well, let's then just jump into the proof of this theorem. So what's going on here? So first, so we have G acting on X, and we want to prove this identity, and we want to prove that it holds if and only if theta is G equivariant. Okay, so let's start with a vector field. Then, by definition, it's equivariant if and only if it commutes with rows. So row G for all the G's, and that's true if and only if it commutes with the AG stars for all the G's, and that's because AG, as we saw, AG inverse star is just rho G, so nothing going on there. Okay, so then let's look at the, so now this is true. So this is an equality of derivations of k brackets x. So in particular, they have to be true whenever we plug in a polynomial or a function on x, and then apply this derivation and then plug in an element of little x. So we do that to both sides. So what do we get when we do these operations here? Well, at the very end, we're doing AG star. So that means we apply G to the input. So we do G of X, and then we do theta of F. What about over here? Well, here we're doing precomposition with AG star. So what that means is we're taking the differential at X, so X is the final input, the point where we're working. We're taking AG of X, and that's a linear map from the tangent space at X to the tangent space at GX. And we're feeding into that linear map, we're feeding the state of X, which is a tangent vector at X. And the output is something in the tangent space of GX. So in particular, that's a linear map that's a derivation from k brackets X to the field. So we can plug in F there. Okay, so so this is just the vector field. So we have the vector field theta. We look at its value over point GX, and then we plug in F. And then, yeah, and this is nothing changed here. But since this is true for all F, this means that theta sub GX, so the value of that vector field at GX is the image under the differential of the action map of little g of the value of the vector field at X. So I guess maybe intuitively what this is saying is that if something is G equivariant, then if we apply the G action, then that determines. So if we have one point and we want to know what the value if we know the value of an equivariant vector field at one point, and we want to know its value at G of that point, then all we need to do is apply the differential of the G action to get the value of the vector field at GX. So hopefully that's clear, and the notation is something you're getting used to. Okay, so what about the second claim? Well, there's actually not that much to show, because if you're convinced that whenever we have so if you're convinced by the example that I showed earlier that the derivations form that equivariant derivations form Lie subalgebra of derivations of an algebra A, then that follows immediately. Or you can try to show it directly. it's straightforward. And what about this last claim? Well, okay, so in the last claim we had not just any G space, we had a principal homogeneous space, so transitive action with no stabilizers. So that means that for any little x, we get an isomorphism of varieties from G to X, given by taking G to G cross X. So we kind of get so X is like, it's isomorphic to G, but there's no distinguished identity, there's no distinguished base point. But anytime we pick a point, then that gives us an isomorphism between G and X. And so we have an induced isomorphism between the affine algebras. And what we can do, so what we want to do is, so the claim is that if we had any equivariant vector field on X and we specialize it to a point little x, then we get an isomorphism between the space of equivariant vector fields and just the tangent space at that point. So what we want to do is show that this is surjective. So let's define an inverse map. So if we start with a tangent vector at little x, in other words, the derivation from k brackets x to k little x, let's define an endomorphism of k brackets x, and then we'll show that this endomorphism is actually a derivation. So how do we define this endomorphism? Well, we do A star, this pullback by the action map. And then in the first coordinate, we apply this, the inverse of this algebra isomorphism phi, or psi, sorry, psi. So then we land in k brackets x cross k brackets x. And then we apply this, tangent vector on the first coordinate. So we get something in the field tensor k brackets x, but we can get rid of that first tensor factor, and it's just isomorphic to k brackets x. So this is a linear map from k brackets x to k brackets x. So this is kind of maybe the diagrammatic way to think about what it is. You can think about it in terms of equations. So this is what it does in terms of equations. So if we know that the action is transitive, so anything in x is g dot x for some unique g. And if we want to define this map S, so we want to take a tangent vector and define an endomorphism. So we apply, we take an f in k brackets x, and we apply this, and so that's some other function on x, and its value at g cross x will be given by the following formula. So we apply we start at x, we apply the action map of g, we differentiate the action maps, and then we feed in the tangent vector xi. So now we have a tangent vector at gx, and we can feed f into that tangent vector to produce an element in the field. So that's maybe that's possibly more concrete, possibly more confusing way of saying what this map is. So now there's some things to check that I won't go through. So first of all, this is actually derivation. That's not too hard to show because we know that this tangent vector is a derivation. And second, that it's G equivariant. And that's also not too bad. So yeah, because it basically follows from part one, because we kind of defined this vector field so that the identity in the first part of the claim or proposition or whatever is true. And it was if and only if, so it must be G equivariant by definition, pretty much. So yeah, so that's this result. I wanted to point something out. You may be wondering, what if the action is transitive but if you have stabilizers? So there things are more subtle. But if the stabilizer is a normal subgroup, then so if x is G mod H, then you can use essentially the same proof. You have to modify things in certain places to make this map S well defined, but you get the same result that equivariant vector fields on X in this case would just be determined by their value at a point. Of course, if H is normal, then G mod H will be another group. So yeah, so you can think about it from that perspective, but it's still true. So this is just a remark. Right. So now we want to move towards defining. So I mentioned at the beginning of this lecture that we want to associate a Lie algebra to any linear algebraic group. So let's move towards doing that. So if we have a linear algebraic group, then we have these actions of left and right translation, as we mentioned before. So left translation is just left multiplication by X, right translation is right multiplication by G inverse. Sorry, maybe I said X here, I meant G. And so these are, yeah, this is an action of G on itself. Both of these are actions of G on itself. So it makes sense to think about left and right invariant vector fields on G. So a left invariant vector field is a vector field that's equivariant for the left multiplication action of G. So in other words, it commutes with with all these LG stars. So LG star is the induced pullback map on the level of functions. And for right invariant, we do the same thing except for the R's. So our theta has to commute with the RG stars. So for right invariant vector fields, that's equivalent to asking that theta commutes with the rho G's that we saw in previous lectures, and the theta commutes with the lambda G's that we saw previously. All right, so those are just definitions. So we know they're Lie algebras because they're vector fields that are equivariant for a group action. Okay, so the claim is that they're isomorphic as Lie algebras. So to do this, one thing we need is the antipode map. So remember that there's the inverse map G to G that takes X to X inverse, and the corresponding map on the level of algebras is the antipode map. So the notation was S. I think Springer uses some different notation, but I'm used to calling it S. So I used S in these notes. So the map, so the claim is that if we have a right invariant vector field, then if we conjugate it by S, so if we apply S, so S squared is equal to 1. So if we apply S to, if we precompose and postcompose by S, then that will be left invariant. And not only would that be left invariant, but this will give us an isomorphism between these two Lie algebras of left and right invariant vector fields. So how does it work? Well, first of all, yeah, so as I said, S is the pullback under the inverse map. Then first of all, you can check that we have these following two commutative diagrams. So if you do the right action, so X goes to X G inverse, and then you apply I, then you apply the inverse, so then you get from X G inverse to G X inverse. That's the same as first doing the inverse and then applying the left action. Or you could have done it with the left and right reversed. So yeah, so that's, you just write it out and you'll see that these two diagrams commute. So we'll use this in just a second. So we need to check that phi is well defined. So in other words, that it lands inside the left equivariant vector, left invariant vector fields. And why is that the case? Well, we use, so because, okay, so let's check. So we take the image of phi of, so theta is right invariant. We apply phi, so we get S theta S. And now we want to see that it commutes with these LG stars. So we write S as the pullback under I, and then we use the commutativity of these these diagrams, I guess we use the commutativity of the left one here to turn the L into an R. So we have this, so we use it in this equality. And then we do the pullbacks again, the functoriality of the pullback map. And since theta is right invariant, we can pass it through. And then again, we use this the fact that S turns R's into G's, R's into L's, and L's into R's. And we get the LG star popping out on the other side. So there we go. So that proves that it's left invariant. And why is it a map of Lie algebras? So I didn't spell this out, but it's actually pretty simple because S squared is the identity. So if you take theta and theta prime, then if you write out what the commutator is, then you have the commutator of the image of theta and the image of theta prime. Then you have S theta S composed with S theta prime S, but the two S's cancel. So and that's in both factors. So yeah, if you write it out, you see that we get the right thing. And yeah, and it's also an isomorphism. I guess this is because I guess there's various ways to see this. This is one way is because they're yeah, I guess the easiest way is just to do directly to show that in fact, if we take a left invariant vector field and do the exact same map, take it to S composed with theta composed with S, then we get a right invariant vector field. Or we can use an automorphism of the group that takes left translation to right translation. So yeah, there's various ways to see that it's an isomorphism. Or you can observe that these are both actions, both transitive actions, both torsors, so transitive actions with no stabilizers. So they're both determined by a point, and you can look at what happens at the identity. All right, so so those are two. So now we've associated ostensibly two different Lie algebras to the group, but they actually turn out to be the same. So there's another way to think about this Lie algebra, another manifestation. So to set things up, let's first consider again the coproduct map. So the multiplication on G, pullback of multiplication on G gives us a map from affine algebra of G to the tensor product of two copies of the affine algebra of G. That was just the coproduct that we've worked with. And there's also the co-unit map, so eta. That's evaluation at identity. So so the affine algebra of G is a co-algebra, as we saw. And what happens is that if we take any co-algebra and we look at its dual vector space, then that has an associative algebra structure on it. So the co-algebras become algebras undertaking duals. And so in this case, so we're interested in the dual space of the affine algebra of G. So just all linear Helms from Kg to the field. And the algebra structure is given by precomposition with the coproduct. So if we have two functionals on Kg, then what's their product? Well, their product will be, well, it will be another functional. How do we get it? Well, we first apply the coproduct, then we apply the functionals on each of the two factors. So that's what's going on here, and that's the product in this algebra. And the unit of this algebra is the co-unit as a linear map from Kg to the field. Okay. So so this is maybe a bit of abstract nonsense. Hopefully it makes some sense at least. So yeah, and the proof is just so you need to show that this is associative, but that follows quickly because delta is co-associative, and you use the co-unit axiom to show that this is actually a unit. All right. So okay, so we have the dual of the affine algebra of G. This is an associative algebra. So it has a Lie algebra structure given by the commutator. So we just do this operation in the reverse order, take the difference, and that's the Lie algebra structure on the dual space of the affine algebra of G. And now the claim is that if we look at derivations, if we look at the tangent space at 1 to G, those are derivations from K brackets G to K, maybe I should have written 1 here. So they're derivations from Kg to a one-dimensional module. So in particular, they're linear maps from Kg to their linear functionals on Kg. So they live inside this dual space. And the claim is that this tangent space is actually a Lie subalgebra of this big dual space. So this space is really big, but the tangent space is something finite dimensional living inside, and it turns out to be a Lie subalgebra. Okay, so let me give, I guess this will be more of a sketch of a proof. So maybe some of you are familiar with Smoothness notation. So when working with coalgebras or Hopf algebras, it gets kind of messy writing out all the summations when we do the coproduct and all the indices and so forth. So it's so kind of a shortcut is just to write the coproduct of A as A1 tensor A2. So there is implicitly when you write this, you should keep in mind that there's a summation going on here, but this notation usually suffices for most purposes. And if you ever need to, you can go back and write the indices, but it's much clearer just to write it in this way. So that's Euler notation. Okay, so if we using Euler notation, we can write this product of maybe this. Oh no, this is fine. So we can write the product of two elements in the tangent space. So thinking of them as linear functionals on Kg, we can write them in the following way. We can write this product in the following way. So if we want to know the value of this functional at A, so A being an element in K brackets G, well, that would be the product of so again, there's a sum here, but that would be the product of xi applied to A1 and xi prime applied to A2. So, and again, there's a suppressed sum here that this is over all the simple tensors that appear in the coproduct. Okay, so we want to show that this is a derivation. So let's take, well, okay, we'll eventually want to show that the commutator is a derivation. Let's first compute what the product is of these two applied to a product of elements in Kg, and then we'll look at the difference between xi times xi prime and xi prime times xi. Okay, so this is just a computation here. So we know that, okay, by the previous line, we get that this is as follows. So A1, B1, so that's because the coproduct is an algebra homomorphism. So we get xi of the product A1 and B1 and xi prime of the product A2 and B2. But we now we use the fact that each of these is a derivation. So we get A1 times xi of B1 plus B1 times xi of A1, and then similarly for xi prime. So then I skipped the steps here, all the ugly computations, but I can just tell you what you need to use. So you need to use the fact that this action here is via the co-unit. So A1 acting on the image of xi of B1 under xi so this image is just a scalar. So A1 acts on that scalar by the co-unit map. So we get, we'll get that'll eventually correspond to this A here. And then we also need, so I think I have so I wrote it out here. So we'll also need the fact that if we have 8 of A1 times A2, that's just 8 of A. So again, there's this summation that's suppressed here, but that's just the co-unit axiom. And actually, and here's another. So actually, the second line is really the co-unit axiom, and the first line follows from the second line, because we just apply eta to all sides of the second line, and we get the first line. So maybe I should have written them in the reverse order. But the second line is just the co-unit axiom. And if we do all that, then we get that this is the following expression. So we get eta of A times xi prime of B plus eta of B times xi prime of A plus some other junk here. But we see that this junk is very symmetric. So we have xi of A, xi prime of B, xi of B, xi prime of A. And so then, yeah, I guess we also use the fact that these are k-linear, so you can pull in these eta values inside. And so then if we actually compute the commutator, then we'll have so the stuff over here looks good, because when we apply the commutator, we'll get the difference of the xi's multiplied in the reverse order. And so that part is nice, but then we'll get a cancellation of this junk, because when we do them in reverse order, we'll get xi prime. So we'll have a minus sign, and xi prime times A, xi times B, and that'll cancel with this term. And then we'll get another term that cancels with this term. So yeah, it's just a bunch of computations, and you can go through it and convince yourself. Right. Any questions though? I can still explain some things if you want me to. I don't want to get too bogged down by all the formulas though. All right. So let's just keep going then. So, okay, so the upshot of all this stuff is that we get a Lie algebra structure on the tangent space. So again, just to summarize, we started with the co-algebra structure. So we started with the group structure on G, right? So this is kind of a direct line from the group structure on G to the Lie algebra structure on the tangent space. So from the group to its Lie algebra. So we started with the multiplication on the group. We thought about the pullback map on the level of algebras. That gave us the coproduct map on the affine algebra of G. Then we thought about the dual space of this affine algebra. So it's some big infinite dimensional thing, but it has an algebra structure. So the co-multiplication, the coproduct becomes a product on the dual. And inside this dual, this big thing, we identified the tangent space at the identity as certain k-linear functionals on the affine algebra, those that are derivations onto a certain module. And that had a Lie algebra structure. And that's what we're going to refer to when we, that's what we're going to refer to when we say the Lie algebra of G. So we'll write this math frac G for the tangent space, equipped with this Lie algebra structure coming from the associative algebra structure on the dual space of the affine algebra of G. So it's kind of maybe complicated, all these steps, but it's a direct line from G to its Lie algebra. And from G to it's the Lie algebra structure on its on the tangent space at the identity. So of course we can just take the tangent space at the identity, but the Lie algebra structure is not clear until we do this sort of procedure. There's other ways to see it though. Okay, so how does this Lie algebra relate to the ones we saw before with left and right invariant vector fields? Well, so we have this result here that if we take so basically evaluation at the identity is an isomorphism of Lie algebras from left invariant vector fields. And more precisely, if we have theta left invariant vector field and we post-compose with eta, which is just evaluation at the identity, then we get, obviously we get a tangent vector at the identity, but this is a isomorphism of Lie algebras. So, So I decided to give this as an homework exercise. I'll have a bunch of hints, so hopefully it won't be too bad.
Just
I
what
should
is
say,
written? I didn't understand just what is written on the right-hand side of the map.
um,
From Lee G.
over here,
No, previous line, previous row.
this. Oh, this is mathfrak G. This is the mathfrak G. So we're going to write mathfrak G for the tangent space at the identity, equipped with the Lie algebra structure that I just described. Does that make sense?
Okay, so what is written on the left-hand side?
These are the left invariant vector fields on G.
Okay, thank you.
Yeah, so once you prove this proposition, we'll have seen so far 3 different manifestations of the Lie algebra of G. One is as left invariant vector fields, one is as right invariant vector fields, and one is as a tangent space with identity with this Lie algebra structure coming essentially from the multiplication action, from the multiplication map on G. And they're all isomorphic as Lie algebras, but depending on if you're on what you're working on or what you want to prove, you'll maybe want to prefer one of these manifestations to another of these manifestations. Also, I wanted to say, so so to me personally, this tangent space at the identity argument going through the dual of the affine algebra makes kind of most sense because it's canonical. With left and right invariant vector fields, they're isomorphic as the algebras, but there's this choice of left versus right, which there's no canonical choice of left invariant versus right invariant. So that's why it doesn't feel quite as canonical to me. Whereas in the books, so in Springer, I also looked at Humphreys. So Humphreys has a nice section. They define the Lie algebra as the left invariant vector fields. So they make this choice from the outset. And yeah, so this lecture so far, I've been only vaguely following the book. So it's mostly not things that appear in the books, but maybe said in a different way. So that's why I'm not going to have homework exercises from the book for this lecture, but I'll give you some exercises that I'll post on the website or send you by email. Anyway, yeah, so that'll be for you to think about. And yeah, so I guess I already kind of alluded to this. So we have these 3 Lie algebras and they're all isomorphic, and we have these explicit isomorphisms. So we have, so from left invariant to right invariant, we conjugate by the antipode. So we saw that. From left invariant to the tangent space at the identity, we evaluate at the identity. From right invariant to tangent space at the identity, we evaluated at the identity, but then there's this pesky minus sign that we need to include. So yeah, when thinking about this minus sign, it doesn't affect the Lie algebra structure. So in fact, there's this general fact that you can think about, that any Lie algebra is isomorphic to its opposite via the minus sign, so multiplication by -1. And this is, I guess I didn't say what opposite means. Opposite just means you, instead of, so the opposite bracket would take x and y to y, x, the bracket of y and x of the original bracket of y and x. So the opposite bracket of x and y is the original bracket of y and x in that order. But it doesn't really change anything because we have this isomorphism. So yeah, so that's kind of the summary of what we've explained so far. So this maybe feels a bit abstract. So let me try to address the following question. So can we describe this Lie algebra in terms of generators and relations? So you've probably, I'm guessing many of you have seen Lie algebras before, and you've seen them given by generators and relations. So how do we see those generators and relations coming from this more algebra geometric perspective? Okay, so so this would be kind of a partial answer. Of course, I can't give a complete answer, uniform answer for all the algebras, but let me kind of give you the idea of the procedure you would do for any specific group. So if you have a linear algebraic group, it embeds into GLN as we've seen. So then the first step is to understand the Lie algebra of GLN. So the tangent space at identity with this Lie algebra structure. And since this, since GLN is an open subvariety of n by n matrices, based on the stuff with tangent spaces and whatever that we saw last lecture, we have an isomorphism between the tangent spaces at identity. So this is true for any open inclusion. And one thing to note is that, okay, so we want to understand this Lie algebra structure on this tangent space, and it was coming from a associative algebra structure on the dual of functions. Now, how can we retain any of that with these matrices instead of GLN? Well, it pretty much goes through. So matrices have a multiplication structure. And that gives a co-algebra structure on the affine algebra of matrices. So we have a coproduct map and a co-unit map, which is evaluation at identity. But the difference is that we have no antipode because there's no inverse map of matrices in general. So this is only a co-algebra, not a Hopf algebra. So we have all the axioms of a Hopf algebra except for the ones involving the antipode. But it all works out. And we have an induced algebra structure on the dual space of the affine algebra, like so. So just like we saw before. And you can check, it's pretty much the same proof, that the tangent space at the identity of n by n matrices is a Lie subalgebra of this dual space. So it's the same, pretty much the same proof as before. I think in that proof we didn't use the antipode or the hexagon axiom or anything, so it's fine. And so we get a Lie algebra structure on this tangent space, and the isomorphism with the tangent space at the identity of GLN is an isomorphism of Lie algebra. So this is an isomorphism. I guess I should have put a star here. This is what I meant. So this is an isomorphism. Okay, so that's kind of some formal stuff. So we basically reduced the problem to understanding the tangent space of the identity of n by n matrices. And this is easier to understand because so first of all, the affine algebra is just polynomials and some variables, Tij, I and j run from 1 to n. And so to understand what's going on here, I claim that there's a injective algebra homomorphism from n by n matrices to the dual of the affine algebra of n by n matrices. So this is kind of maybe a bit weird. There is another there's another injective algebra homomorphism that you may be thinking of if you're familiar. This is not quite that one because I want to make sure everything is a derivation. So this is also one thing to point out. So maybe you've seen that an algebra homomorphism doesn't necessarily need to send unit to unit. So this does not send the unit of matrices to the unit of this. I guess it's the co-unit as a linear function. But anyway, that's some technical stuff. So what is this map? Well, if you take the elementary matrix Eij, so one in the ith row and jth column, zeros everywhere else, then I want to map it to what I'm going to call xi ij, which is the following linear functional on this algebra of polynomials. Well, we take the partial derivative with respect to Tij, and then we apply the co-unit. So it's pretty simple, and it's actually easy to see that it's the image. So all of these together span the tangent space at the identity. Yeah, so we have that, and so, but we need to show that this is an algebra homomorphism. So to see that it's an algebra homomorphism, okay, how do we need to take two matrices, elementary matrices, multiply them, and move them over under this map, and compare that to what we would have done if we moved them over and then multiplied them. So if we just multiply them, we get this sort of thing. So EIJ times ERS is EIS, is if J and R are the same, otherwise we get 0. Okay, so what about when we move them over and then multiply them? Well, when we move them over, we have this expression, and we can only figure out what it is based on how it acts on where it sends the generators of the polynomial algebra. So if we take some generator, and where does this send that generator? Well, in order to compute it, we have to we'd first do the coproduct of that generator. So that's this thing here that we've seen before, this expression. And then we apply each of these to each of the factors. So we have this expression. And now here, if we go back to what the definition of these xiij's are and what the definition of the xirs is, so there's some partial derivatives, right? So we check what those partial derivatives do, and it's pretty straightforward to see that this is 1 if u is equal to I, so if these two indices match, and s is equal to v, so if these two indices match, and j is equal to r. So that means that for some w, so j is equal to, so there's some w that's equal to the common value of j and r, and that'll give you a 1 here. But if those conditions are not all satisfied, we get 0. And then if you think about it, that's the exact same thing as this operator applied to TUV. So we have IS and then JR here. So, and that's what we would have gotten if we mapped over the multiplication of these two elementary matrices. So this is just a bunch of linear algebra. Then injectivity is maybe, if it's not clear, then I think it's easy to show. And we know from the last lecture that this vector space is spanned by these derivations. And so what we get is an isomorphism of algebras between n by n matrices and this tangent space at the identity. So something special, very special, is going on here, which is that this tangent space at the identity of n by n matrices is actually an associative algebra. It's more than just a Lie algebra. But it doesn't happen for a general group. But that's something special here, and it means that, okay, so what are the conclusions here? So the conclusion of all this discussion is that we can identify the Lie algebra of GLN through this procedure of thinking about n by n matrices with the Lie algebra corresponding to the associative algebra of n by n matrices. So it sounds kind of confusing, I guess, when I say it, but it all kind of fits together. And GLN is n by n matrices, which, as we know, is an associative algebra, but we think of it as, so we think of frac GLN as the Lie algebra of n by n matrices with the commutator. Okay, and if we, I said, maybe I shouldn't have said general linear group. So if we take an arbitrary linear algebraic group, then it'll be some Lie subalgebra of the Lie algebra GLN, of frac GLN. So it'll be some Lie subalgebra of n by n matrices that won't, in general, be an associative algebra. Yeah. So that's what's going on here. I guess if you're familiar with Lie algebras and Lie groups and how you get Lie algebras from Lie groups, all of this is maybe seems overly technical, but to be precise, to kind of give everything from the ground up in terms of algebraic geometry, this is how you do it. So some examples. So so for SL2, so these will be, we already saw, so last time we computed the tangent space of the identity of SL2, and we saw that there was an identification with traceless matrices. If you think about how that identification worked, that's exactly saying, that exactly matches this identification of the tangent space of the identity of GL2 with n by n matrices. And so we get this trace zero condition that we had before. And the generators are, you can think of them as these three matrices. And if you write out the relation, so we just compute the commutators of these matrices as appropriate, then we get these SL2 relations that are fundamental to
Can you explain again?
representation theory.
Can you
Sure, let me just, I'll stay on, but let me just end the class and remind everybody that no class next week, and we'll meet again in 2 weeks. And I'll email you homework questions, and feel free to email me if you have any questions. So yeah, thanks. And